Welcome. First, yes, colloquium in person. Good to see you guys all. And today that Rishab from MIT, so he's a postdoctoral researcher at MIT. And then prior to that, he was the Apple research fellow at the Simmons Institute for the Theory of Computing. He received a PhD from UT Austin with the best thesis award. Welcome Rishab, and now let's start.
Thanks a lot, Sankar, for the introduction, and thanks a lot for being here. I guess in COVID times, it's interesting to sort of just see people in person and sort of just give them. So, all right. So, thanks you so much. And today I'll be telling you more about advanced cryptography. So, one of the founding goals in cryptography was to enable. Secure communication. Back in the day, it relied on techniques such as secret handwriting, covert physical devices, and lockboxes, and many other such mechanisms, whose basically foundations were based in puzzles, permutations, and the general perception of what was physically possible and impossible to do in those times. While it was great for that era, it did not provide us any provable guarantees. This soon changed with the introduction and the discovery of public key cryptography in the 70s, where now we ushered in a new era of secure communication, where we could get provable security in presence of a wide variety of attacks. And this led to formalization of many new concepts in systems such as encryption schemes, signature schemes, proof systems, and much more. And one of the most attractive features of the system was their security, their hardness. The security could be based on the hardness of well-studied mathematical problems, such as I could give you a system such that if you could attack that particular system, I would be able to give you an algorithm to solve factoring in polynomial time, which we still don't know how to solve unless you have a quantum computer. And we'll get to the quantum debate a little bit later. But the fascinating point was we can get provable security from well-studied hard assumptions. And this soon led to sort of multiple applications in so many devices or so many things that we are using currently, like different blockchain services or signature applications and much more. And intrinsically, these concepts are also sort of part of many technologies that we use every day, but we don't even realize. So what I'm most fascinated by, is there something beyond public key cryptography that we can study? Is there something sort of beyond the realm of the current cryptographic feasibilities or sort of availabilities that maybe we can sort of just use for our advantage? But before even trying to understand what lies beyond public key cryptography, a simple question is, why even study that? So the answer is that the recent technological and scientific advancements, they have sort of gave us very powerful systems which have advanced features. And those powerful systems with these advanced features are no longer securable just using public key cryptography. And even with the laws and policies around us that are available for our protection, even then we cannot sort of fill the gap that is left by public key cryptography and law. And for that, we really need to look beyond what's possible in public key cryptography. Let me give you a few simple examples. So consider an example where we have a medical facility that's storing a large database of patient records. And under the HIPAA law, we want privacy for all these patients. Now, if we ask our very own good crypto oracle, it's going to say, you use encryption and you can get privacy for all these records. That's great. But what if the facility says, I also want to stop insider attacks from my system? What can you provide in that case? An insider attack is basically when a person who is authorized to recover information gets access and basically starts leaking that particular information. What can classic or just public key crypto give us? It basically goes silent in this case, and it leaves us with just two options. Either we have to sort of disallow access for everyone. That's bad because then we can't use the functionality of the system. Or we have to sort of just live with the concept of there will be insider threats in the system. Now, there are so many more examples, and let's just look at another example of software patching that sort of we look at every day. Typically, so many softwares are sort of patched every day, where many of these software patches, they claim to sort of fix some security vulnerabilities in the previous version of the software. And a big problem is that how to release these software patches that can hide the vulnerability, such that an attacker cannot use that vulnerability in order to attack the unupdated systems. Now, in this case, if we go to a crypto oracle, then the oracle is completely clueless and it provides us nothing. Unlike the case of encryption, where we had at least something for privacy, here we get nothing. And we are basically left with two unsatisfactory options. Either you do not patch the code, leaving the code vulnerable as is, or you patch the code, potentially leaking the vulnerability that was present. And there has been a recent push in trying to sort of get better laws trying to force people, the software providers, to release patches so that the code is no longer vulnerable. But even with those laws, there will be a gap because we will not be able to secure these vulnerabilities. We will not be able to hide that information. Now I can keep on going and tell you many more examples in which we can try to sort of secure many more applications, such as trying to perform intricate computation or reducing the amount of cryptographic storage, and many other such applications where the traditional lens or the traditional view of public cryptography or the current capabilities is very limited. And the point is that we really need to look beyond public cryptography. And what lies beyond public cryptography is typically what we call the advanced cryptography space. And it claims to sort of contain many fascinating and mythical concepts which can provide a security and fill these amazing gaps. For example, if we look back at the example of insider threat problem, if we ask our advanced crypto oracle, hey, I want to stop insider attacks, then the advanced crypto oracle is going to say, although it might seem it's impossible to stop insider attacks because cryptography is sort of just foundationed in the concept that you have to keep your secrets secret, otherwise you get no security. Here I'm saying, even if you reveal your secrets, then can you give me something? While it seems counterintuitive that how can you sort of prevent such attacks? Advanced crypto says there's a new angle to solving this problem. I can give you something called traceable encryption, and traceable encryption is going to give us a mechanism, a third option, in which we can identify the users who have been compromised. Once we identify them, then we can make them be held accountable. So you get accountability and privacy in a single system. Similarly, if you look at the example of software patching, advanced crypto gives us an amazing concept called code obfuscation. And code obfuscation is basically a compiler which takes us input a program and it compiles that input program into an obfuscated version of the code that claims to hide all implementation details and all the secrets from the input program, thereby giving us a mechanism to hide the security vulnerability in the release patches. And the point is that this space contains amazing systems with advanced properties that can provide security in this regime. And the premise of this talk is that this space is possible. It does exist and we can get to it. And the idea is that similar to how public cryptography revolutionized ancient cryptography back in the day, advanced crypto has the same potential to revolutionize what we can do using public crypto. And that's basically my vision, because I want a future in which advanced crypto is available to everyone in the world. And we can potentially have advanced crypto available on every device, similar to how ubiquitous public crypto currently is. Advanced crypto should be available to everyone. The reason is that routinely we sort of just end up with this option using just public cryptography. We either have to sort of pick functionality or security. We can't seem to get both. But with advanced crypto, we can unlock this third option, this option C, which says you can get functionality and security in a single system at the same time. And that's basically the power of advanced crypto. In my research, I basically focus on these well-studied hard mathematical problems. I anchor myself to these problems and basically sail towards this advanced crypto and try to visualize that how can we embed interesting algebraic structures that satisfy some type of hardness, but can be used for cryptographic purposes. And in my research, a special focus of mine has been to focus on the problems of lattices, integer lattices, because integer lattices, the hard problems regarding integer lattices, they're known to be post-quantum secure. And we don't have any post-quantum attacks on that. And they're also the basis of NIST post-quantum standardization. They're the leading candidates which are being used in that standardization process. And even further, lattices have incredible geometric structure, which has been shown very powerful for building advanced cryptography that is not shared by other number theoretic and coding-based assumptions. So in my work, I have built a wide variety of advanced cryptographic systems, ranging from encryption systems, signature schemes, proof systems, and much more, which serve different properties and provide us advanced security and advanced properties in light of these existing attacks. And today I'll mostly focus on my work on traceable encryption and tell you how traceable encryption gives us a new approach to solve the insider threat problem. And this would be a good time to ask questions if anybody has questions about what advanced crypto is and what is the feasibility of it. Otherwise, I'll basically move to the part about discussing traceable encryption. All right, so okay.
So question, in the case of advanced crypto, is NIST thinking about that? Who's thinking about it other than you? Or is it just in quote unquote so new that?
It's not so new. It's people are thinking about it, but the big problem is that sometimes the things that we can build, this seems so counterintuitive that people feel like that's not even possible. And that's basically people go like, okay, hey, I can't even, maybe that's not even possible. Why even ask a cryptographer whether it's possible or not? And people have been thinking about it. For example, there's going to be the notion of aggregate signatures, which I might get towards the end of my talk. That's something that's actually being deployed in blockchain protocols these days, trying to compress the large blockchain space into smaller spaces using these particular cryptographic techniques. Yeah. Yes.
I don't know if you're going to talk about it, but sorry if I'm asking you so. What do we need encrypted testing?
Why do we need encrypted testing? Hold that question. I'll maybe sort of get to that towards the end of the talk. Yeah.
I'm sorry, could you repeat her question, please?
So her question was, why do you need encrypted testing? What's the benefit of encrypted testing? I said that it's a great question, but I'll probably sort of just, yeah, the application is more sort of just geared towards what we can discuss towards the end. All right. So let's move on to traceable encryption. And I'll tell you basically, the first part will be telling you how to formalize the notion of traceable encryption and how it sort of gives us a solution to sort of finding, sort of avoiding the problem of insider threat. And in the second part, I'll just tell you the history of the concept and the result that we're able to show. And finally, how to actually get this result. What are the main technical ideas behind it? Now, in the first component, let's just revisit the problem of insider threat. So recall the insider threat, somebody who sort of authorized to decrypt something gets corrupted. And this problem is not sort of localized to medical facilities, but this problem is all around us. Imagine any system where there are a set of authorized users. It could be a health records in a hospital. It could be an education records. It could be defense database and military network. It could be broadcast TV or streaming services and much more. There's so many more applications where we can sort of just have these insider attacks. And the point is that to prevent such or prevent sort of get privacy and prevent such attacks, we already have interesting laws in place such as HIPAA, FERPA, and much more. And despite these laws, public key crypto does not complement these laws enough, and these insider threats are still sort of very pervasive in our society. Traceable encryption, or sort of just traded tracing, it basically says, I can give you a scientific mechanism to sort of bridge this gap. And the idea is that I'll give you sort of this idea of tracing the identity of compromised users. Once you can trace them, then you can make them hold accountable. But let me formalize, how do I sort of kind of trace it? I mean, it's very unclear. How can you sort of figure out the identity of people who have been compromised? The idea as follows. So let's just consider that we have an encrypted cloud service available to us. And there are 5 users who are sort of authorized to decrypt that particular information, recover that information. And I'm just taking the example of an encrypted cloud service just for illustrative purposes. It could be a small scale terrestrial network. It could be as wide as a satellite communication channel. But anywhere where there are certain set of authorized users who are allowed to sort of recover some encrypted content. So just take this encrypted cloud server. And the idea is that all these users, they have their private decryption keys in order to access this particular encrypted content. Now, in an insider threat, what happens in an insider attack, suppose an insider corrupts an attacker corrupts Charlie and David. It gets these particular keys. Now, using these particular keys, what the attacker can do is that attacker can create something called a pirate device or a black box. And the idea is that this black box can also communicate with the cloud and can recover the encrypted content. And this black box could be anything. It could be an algorithm posted on a public bulletin board. It could be a device sold on the black market, or it could be a web server hosted somewhere totally in an inaccessible area to us. The point is that some service, some mechanism to recover encrypted content, and I don't even have any sort of control over it. Traceable tracing or traceable encryption basically says that there is a mechanism to just look at how this device is behaving with the network, how it's interacting. And just by looking at that communication, you can figure out the identity of the users whose key was compromised in this attack. For example, in this case, I can figure out that Charlie's key was used in creating this particular device. And that's the way I can sort of hold Charlie accountable for this particular attack. Or say, okay, hey, your key has been compromised. Now let's just try to formalize a little bit further what are the properties that we might require from such an encryption system. Clearly, we would want the first property, 2 properties will be, if this device does work in recovering the encrypted content, then we want to have the ability that we should always be able to catch someone. And you should never falsely accuse anyone. Otherwise, it's not very useful. Additionally, it's very important that we allow adversaries to perform any arbitrary attack. Allow them to corrupt as many keys as they want because they can potentially bribe those users. We don't want to put any restrictions on the attacker. We also don't want the system size to grow with the number of users. Say the number of users in the system is 1 million. Then we don't want the size of the ciphertext in the public keys in the system to grow as large as 1 gigabyte because that can't be supported at all and it's not very scalable. Moreover, we don't want to assume that what's the structure of this black box. I don't know. It's an algorithm. It's a website, which I can't even look over. It's a device, a hardware device, which I can't even open up. It could be sort of somewhere in any arbitrary physical form or location. And along with all these properties, I also want to get provable security. And getting all these properties in a single system has been a challenging task so far. But before sort of just telling you about the history of this problem, let me just briefly remark that suppose we have a traceable encryption or traitor tracing system. Then the idea is that traitor tracing system, although on its own is not enough to stop these insider threats, but by combining laws that we already have in place, it gives us a great mechanism to sort of catch these particular insider threats and catch these traitors in the system. The idea is that not only this sort of gives us a mechanism to sort of prevent these attacks, but it also gives us a mechanism to give reproducible evidence so that you can actually show to encode that this is why this user was compromised, because you can just sort of run that algorithm again in a court of law. So any questions about the model of traitor tracing or what sort of we are trying to claim here?
I have a question.
Okay.
So basically, how will you differentiate between how the black box uses the key versus Charlie using the same key?
Absolutely. So imagine it this way. Okay. Let me explain it in very simple words. Imagine that you just got this device from the black market. And if you got this device from a black market, maybe you paid it to someone. Maybe sort of FBI said, okay, hey, I got this device and I want to see whether it's working, whose sort of key it's using. Now, if Charlie is using it in an authorized way, then you don't want to catch Charlie. But that Charlie will be sort of just using on his own device, right? It won't be like a sort of a device that's sold on a black market, or it's like a web server that's posted online. Because that's basically going to sort of contradict with the terms of agreement of that particular use case for that particular user. Does that
make sense? Yeah, makes sense.
A follow-up question to that, Rishab, like, can we have some mechanism in place like packet sniffing to, capture if someone using a black market device with Charlie's private key, can we just do packet sniffing over the network to see if some bits have been changed, but they are using the same secret key to capture if someone is using some other device to access the secret key and get the data back?
You can use those tricks, but the problem is that those are again going to be engineering tricks, and they're not going to give you anything with a fixed guarantee. And plus, you are assuming that the way the adversary sort of recovering this content is the same way you will recover in an honest way. The adversary, this box, could not be using the decryption algorithm. It could be just using any arbitrary technique to sort of recover this information. And that's why it might be sort of just sending out these queries and performing over the network in an arbitrary way that you can't even understand what it's trying to do. But I mean, there are sort of interesting questions, but I guess let's just focus on the case that I give you a device and you have to figure out an identity. And I don't even know how to look in the device. I have to basically, in my mind, read what the device is sort of just doing. I can't even look at the particular code. But yes. So.
Yeah, if everyone has different keys or identities and you have a cloud system, why not just ask them to log into the cloud system, see what their identity is, see who accesses the data, you get it.
Great. It's an interactive solution, and in that interactive solution, you're like, okay, hey, that the server must know in a way that, okay, hey, what you are trying to request. Suppose you don't want that information. It's like a cloud service in which basically everybody is able to contribute, and you don't even want to leak that. So the question becomes quite interesting when you say, okay, hey, I also want to add interaction, then can I get all these interesting properties?
So that way, like broadcast encryption for your...
So broadcast encryption is the right model to imagine these things. Okay. Absolutely, yes.
You previously talked about provable security.
Yeah.
What does it mean in the context of data?
Provable security basically means that once we design a system, we should be able to reduce that its security on well-studied assumptions, and not just say, okay, hey, I give you a system. If you can't attack it, then it's secure. That's basically heuristic security. I just create a system. I have no proof whether that works or not. I just claim it works. That's the difference. A lot of we don't want to end up in that scenario. All right. So if there are no further questions, let's just briefly look at the history of the concept of traceable encryption. So the concept was introduced in the early 90s by Fjarr and Joe Fjarr. And as sort of was raised before, this concept was studied in the context of broadcast encryption and trying to sort of just avoid piracy attacks or just solve the piracy problem in broadcast TV setting. But since then, it has been used in many other regimes. And there have been sort of hundreds of papers being written up about traitor tracing and trying to build traitor tracing, but none of them were able to solve this problem. And despite the limited solutions that we can get for traitor tracing, its applications were already quite significant. The concept of tracing and the weak solution that we had were already used to sort of copyright data disks, and also sort of used in many other areas such as differential privacy, software watermarking, and much more. And given the impact, both in theory and practice, of the concept, the inventors were also provided the prestigious Paris Kanonakis and Theory and Practice Award for introducing the concept of traceable encryption and telling that, okay, hey, you can get accountability in a provable way in an encryption system. And in our work, we were able to show that we can get a traitor tracing system with provable security from a well-studied hardness assumption over integer lattices. And the system satisfies all the wonderful properties that I talked about. The system size doesn't grow with the number of users. It gets all the black box tracing properties and everything. And this was the first system that gave us a secure, a provably secure system, and also a compact system, solving this long-standing open problem. And one of the fascinating consequences of our approach was that since we relied on the hardness of lattice-based assumptions, we were able to immediately get post-quantum security for our solution. So even if tomorrow quantum computers become practical, this solution is still going to be secure because we do not know how to sort of break lattice assumptions using a quantum computer. And in the next part, I'll basically tell you more about how we solve this problem, and which was basically a part of work that appeared at Stock a couple of years ago. And we were able to sort of build the system. And since then, we have realized that these ideas can also be used in many other regimes in traceable cryptography more generally. So any questions about the historical context and what its applications might be? All right. So let's just look at the how to actually get this thing, because it seems like a little bit of a mythical concept. Like, I mean, how do you trace someone? I mean, you can't even look at the device. What are you going to do? So the idea is basically I'm going to break down the problem into two parts. The first part is going to be I'm going to design an encryption system which has some special property P star. And then I'm going to show you that how to basically get this encryption system with this special property P star by developing new structures and gadgets in the geometry of lattices and saying, okay, hey, those structures are still hard. Let's look at the first part just to get a better sense of how to get traitor tracing. The idea is that suppose I have an encryption system with the following property. The property P star is as follows. I have three users, Alice, Charlie, and Emma. And the property basically is I can embed a color in all of these decryption keys. Alice's is going to be red key, Charlie's going to be blue key, and so on. The idea is that when I create a ciphertext, suppose I encrypt hello world that creates a ciphertext CT, and I try to decrypt it using Alice's key, the output is going to be again hello world, but sort of tagged with this red color. If I use Charlie's key, it's going to be tagged with true color, but use sort of the other key, it's going to be tagged with yellow color. Basically, the point is that running decryption on a given person's key is going to give me the color of the secret key in a sense. The output is going to be key color. Now, I claim that if I have such a system, then there is a very simple mechanism to perform traitor tracing. How? So let's just take a simple example. Suppose Emma gets corrupted, her key gets leaked. And using this particular key, an adversary creates a website, and that website uploads, you can upload a ciphertext and get the output back. My tracing strategy is simply going to be, I'm going to submit a ciphertext and check at the color. What's the color? And depending upon the color, I'm going to say, okay, hey, this particular user's key was used in performing this decryption algorithm. That's the idea. It's great, quite simple, but it's quite flawed. And the reason is that the adversary can simply change the color at the last step, decrypts it, changes the color, and avoids detection completely. And not only avoid detection, it can potentially even falsely accuse people. But the problem is, but it more or less captures the intuition that I'm trying to sort of portray, that here we were able to embed some special information binding each user. What if we can also embed some special information in each ciphertext just to make it unique as well? So I'm going to create some special type of undetectable ciphertext or undecryptable ciphertext. And what I mean by that is that each special ciphertext that I can create in the system is going to be undecryptable for one user. For example, I can create a red ciphertext that cannot be decrypted by Alice, blue cannot be decrypted by Charlie, and so on. And now my idea is going to be, I'm going to supply a red ciphertext and see whether it can be decrypted or not. If it cannot be, then okay, Alice was corrupted. And that's basically the strategy I'm going to use. Seems to maybe work, but if we inspect closely, then we're almost done, but not quite. And the problem is that the adversary can potentially corrupt multiple users. Once you corrupt multiple users, you can keep one of those keys to recover the content and say, okay, hey, then I'm going to use it. You can still sort of avoid detection completely. But it turns out this captures most of the intuition. And just to fix this problem, I have to create special ciphertext which don't just make it undecryptable for one user, but for a sequence of users. And then I can sort of trace in a sequence, revoke each person's access one by one, perform some type of randomized estimation on top of it. And using combination of all these ideas, I can execute this strategy to take any encryption system with this special property P star to a traitor tracing system. Just to sort of put it in words, the property P star is that these special ciphertext, they secretly embed an access policy telling whether this particular user can decrypt this ciphertext or not. And the point is, this property P star is enough for traitor tracing. Any questions about how we actually break down this problem of tracing into a more manageable problem about encryption, where we are still trying to hide information inside a ciphertext? Yes.
So I know there's a lot of complex details. I'm wondering, can you give an idea of how it doesn't scale with the number of users?
Imagine that the system that encryption system I'm going to build, that doesn't scale with the number of users. I have not gotten into how it doesn't scale. I'm assuming that the system, this encryption system that we designed with property P star, that has this property about not scaling with the number of users. But that's great. How to build that system? That's a big problem in itself. Yes, absolutely. That's a big problem. All right. So just to sort of recall, you need to keep in mind, the only takeaway is that to get tracing, we need to create some type of special ciphertext, which we can call tracing ciphertext. And in that tracing ciphertext, we can have the special property about embedding a secret access policy. That's it. So now let's look at how to actually get this property P star via lattices. And at this point, I'm talking just too much about lattices, that they're great. They have their amazing geometric structures, post-quantum secure, but what really is a lattice? Lattice basically is a discrete set of vectors in real space over, say, n dimensions. And this is a two-dimensional lattice that I've drawn for you. 0 is the origin in that particular lattice. And each lattice can be specified by n basis vectors. In this case, they can be specified by 2 basis vectors, b1 and b2. The point is that the lattice can be generated by all linear integer combinations of these vectors. These vectors are real vectors, but all their integer linear combinations are going to define the lattice for me. And what happens is that these vectors, which have small length, I call typically the good vectors or the good basis, because you can use these basis vectors to define the entire lattice. Any basis vectors you can use to define the lattice. The vectors which have small length, they are good basis vectors. Which have large length, they are bad basis vectors. And the special property about lattices is that we know from the hardness of lattices that given a bad basis, a large basis, really long, you can't basically figure out a good basis out of it. And just trying to pictorially understand, just imagine a bad basis looks like something like this. In n dimensions, it's going to look even more complicated. You might not be even able to plot it. So you can't really sort of figure it out which are the smallest vectors. And that's basically geometric intuition, why finding a good basis from a large basis is a sort of very hard problem. And why it's very important and useful in cryptography is the following, that in crypto, we can set this large vectors, these bad bases as the public key, whereas the short basis as a secret key. Using the secret key, we can solve some interesting lattice problems that are going to sort of help us in decrypting the message. But given the public key, you cannot recover the secret key. And that's basically the special property about lattices. And that's the security property that underlies most of the lattice-based encryption systems. Now, what's more fascinating about lattice is that in addition to having this amazing geometric structure, they also can be described in an algebraic way that's very friendly. So it happens that you can encode any basis vectors into a matrix of appropriate dimensions. And this basically, each matrix is going to encode basis. And now once I give you a matrix to you, I can ask simple questions about matrix algebra. I can say, okay, hey, I give you a target vector B. Can you sample a vector X such that A times X is equal to B? For simplicity, imagine A is like a square matrix. Can you compute A inverse of B? I mean, clearly you can. You can just do Gaussian elimination, do matrix inversion. The problem is that that's going to give you a pre-image vector X that has really big entries. And that is typically a problem for cryptographic purposes. We can't use it. It's not very useful. But what is useful is that if I give you a good basis, which is also called a trapdoor for this particular matrix A, a good basis corresponding to the bad basis, then that can help you in solving for these vectors X such that X has very tiny entries. It's like a really short vector. And not just for vectors or matrices or just these target vectors. I can also ask the same question for real wide matrices. I can say, I'll give you a matrix P, and can you find a pre-image matrix X such that A times X is equal to B? This is something that we can do using the power of good bases or these trapdoors, lattice trapdoors. That's another algebraic way of imagining how lattice trapdoors are very essential. And just to sort of just let everybody know, the arithmetic that we are doing here is modulo some large modulus q. And that's basically the parameter of the lattice system that we're working with. But it's not very important for the talk, but it's like modulus arithmetic is happening this entire time. So, okay, so what I said was that given matrix X, A, you can compute X such that A times X is equal to B for any B that you can choose. And what's going to happen in my system is that I have to design an encryption system with this special property using the structure of lattices. Typically, I told you a bad basis is what constitutes my public key. But in the traceable encryption system, recall that secret keys, they themselves get leaked. They become like a public information. So I can't typically hide all my information in secret keys. So my first perspective change is that I'm going to imagine my matrix A is going to be secret keys instead of a public key. And this matrix X is going to be my ciphertext. And the point is that if you multiply a secret key and a ciphertext, that's basically going to give you an access policy. So each row of this matrix is going to be a separate secret key. Each row of that access policy matrix is going to be a separate access policy. Imagine access policy is just a color and secret key is just basically the actual key that you have. The property is that we have to create these special ciphertext which secretly embed this access policy. We have to hide B from this matrix X. And before sort of going into that, note that the special ciphertext, they can be sampled using the good base of the chapter of the system. So using that, you can create these special ciphertexts. So creation is not a problem. Problem is, how can we hide information about the policy B in this matrix X? That's basically the goal for the rest of the talk. All right. So let's just again look at this equation. A times X is equal to B, secret keys times ciphertext is equal to access policy. And let's just split it up. So n secret keys as n rows, n policies as n rows. Now I ask you a very simple question. The question is that if I hide first user's key, it's not compromised. I give you all the other keys. Then can you basically tell what's basically the policy that was associated with the first user? What was the color of the first user's key in a sense? Let's just understand it a little more algebraically. So we have these n vectors, sk2 up till skn, that are given to an adversary. We have this ciphertext matrix X. And basically I'm asking, is the first policy B1, is it red color or is it yellow color? Can you distinguish? Problem is that I actually can. I can just define simple equations, linear equations in sk1 and x and say, okay, hey, sk1 in a product with x with all the columns is equal to b1. Similarly, sk1 in a product with all x is equal to b1 prime. I'm going to simply solve these linear equations with sk1 as my variable that I'm trying to solve. It's going to be solvable just for b1, not for b1 prime, because that's how it was defined. And that's basically how I'm going to sort of detect between what was your color. So that's basically the problem, that the standard lattice techniques are not enough because they reveal the policy clearly. But basically our idea is that maybe we can't sort of just get around this problem, but what if we sort of add a little bit of noise? And that might make this problem unsolvable or maybe make it hard to solve. But what do I mean by adding noise to this particular equation? The idea is simple. While creating these special ciphertexts, I'm going to not exactly map it to the access policies. I'm going to add a little bit of noise. I'm going to change the color slightly. And then the idea is that this equation, A1 times X is equal to B1 plus error. The error is unknown to the adversary. Error is unknown to everyone because I just sample it randomly. And that error is going to make Gaussian elimination hard to work for these equations. And this is basically, the reason is that noisy linear equations are known to be as hard to solve as worst case lattice problems. And this has been well formulated as the learning with errors problem in the literature. And this was defined by Oredregev in 2005, but he received the Gödel Prize very recently. The great fascinating problem is that this problem is also known to be post-quantum hard. We don't know how any efficient post-quantum algorithms work for it or quantum algorithms for it. So let me just sort of try to sort of tell you learning with errors problem in other words. So problem is as follows. I sample a vector A, I sample a matrix X, I compute A times X, and that's my vector B. As an attacker, I give you X, I give you B. I tell you, can you compute A? Clearly you can do Gaussian elimination and compute A from X and B. You can just do X in basically in a defined equation, just learn it. The point is that if I add a little bit of noise, and that noise has to be just nicely distributed, circular or sort of low norm Gaussian distribution centered at 0. If I add some special type of noise, which doesn't affect anything else at all, then it basically makes this learning thing very hard. This problem is very hard to learn in that case. I can no longer compute A given X and B. So adding noises makes linear equations hard to solve. And that's basically my intuition. I'm going to say, okay, hey, Let's just add fresh noises to this ciphertext sampling equation, and maybe we're good to go. I mean, that was the problem, right? We could sort of solve it, and that's how we could distinguish it. But it turns out there are some major barriers, major technical barriers when we try to do that. And the barriers are as follows. Know that in learning with errors, this matrix X is sampled randomly over this modulus Q, each entry independently. So X is going to have big entries with all but negligible probability. Whereas in our template, X had to have small entries because it was sampled using this particular trapdoor technique. And that was very essential to ensure that decryption sort of works, that noises do not get amplified when you perform these multiplication sort of steps. Maybe we can solve that, but a bigger issue is that in learning with errors, each entry of X, the matrix that I defined above, that is independently sampled of each other. They have no correlation between all these entries. However, in our template, we have to sample X jointly. It has to be A times X equal to approximately equal to B with this error. Without this property, I can't basically embed a policy in a ciphertext. I need to have this property. And the first property we can this first problem we can solve by assuming learning with errors with small entries is hard. And that's known to be hard by the work of Bonet, Louis, Montgomery, and Raghunathan. But the problem is that the second problem, where X is sampled jointly, that's a major problem. And that's a major bottleneck in all lattice-based systems. That how can you sort of get security while making sure there are enough correlation to the system? Because for security, independence is a very important property. So just trying to understand what's really happening here, we have A times X is approximately equal to B. Point is that we have to sample every entry of X independently to sort of get this type of security. And we clearly can't do that because A times X has to be approximately equal to B. It's crucial we have to embed this. So maybe we are really stuck. But at this point, we think, okay, hey, maybe partial independence could be good enough. What if I don't have full independence about matrix X, partial independence? I can use portion of the matrix X for doing the functionality part, another portion for doing this hiding part, and maybe that might be good to go. I sort of merge these things in a nice way. And that's precisely what we end up doing. We define a new lattice splitting gadget. Typically, previously, we were imagining this matrix A to entirely encode a lattice. Now I'm going to sort of split this matrix A into sort of two sub-lattices. And just imagine that this matrix X on the right, that's split into two components, a top component and a bottom component. Similarly, this matrix A is split into two components, left and a right component. And the idea is that I'm going to sample this right and bottom component independently, no correlations from the appropriate dimensions. A is just random big entries, X is just random small entries, no correlation whatsoever. Special property is that I'm going to sample the left part of the secret key, one part of the secret key to encode a lattice as before. And the top part is going to be sampled using a trapdoor. And that's using that particular trick, I'm going to sort of encode this special information over here. Let me actually show it to you how we actually do it. If we write down this equation, A times X, then we can get the following. A left times X top plus A right times X bottom is equal to AX. That's just basic matrix multiplication. And we know AX is approximately equal to B because that's what we want. So now we can rewrite this equation as follows. We can move the right component to the right side, keep the left component on the left side. And if now you basically focus on this part, everything is independently sampled. A right, X bottom is completely independent, no correlations. And this is precisely what we need for applying learning with errors, assuming that this is a hard thing to solve. Because we want to hide this policy view. If we can sort of add some random looking term to it, that's how we can potentially get security. And the crucial part is that we can use this part to sort of ensure this condition is matched. And we can sample the left part and the top part in a way such that it sort of still ensures that A times X is approximately equal to B. So split a lattice into two sub-lattices and make sure that they sort of align together and merge together. That's basically the trick. Yeah.
Are you generating your ciphertext before the secret key in this example? Like is the right half of your secret key generated after you've already settled on what the ciphertext is?
No.
Okay.
Thanks for the question, but I did not give you enough details. But the ciphertext is generated after the secret keys have been issued because corruption only happens after you give out the secret keys, as probably you were sort of just wondering about. So for creating this ciphertext, all we really need is the good basis. The good basis is defined once you create the bad basis, and the bad basis is basically what the secret keys consist of. So you sample the keys. So typically secret keys are the secret information. The idea is that for the secret keys, I have some more trapdoor information with me, some more hidden information, and that never gets released. I'm going to use that information to create these special ciphertexts at a later point, so that I can potentially trace out, compromise these bad people in the system.
You're saying that this left matrix is derived from the secret keys and within your
The left matrix is my secret key. That's my secret key.
Yeah.
I'm saying the left matrix has like a hidden trapdoor to it, which basically, I mean, you don't want secret keys are not intended to hide something, but basically secret keys are correlated using some special things. And those special things are going to be incredibly useful in sampling the X-top part. That is basically where the good base is coming into the picture. So okay, before sort of moving on, let me just sort of give you a high level overview. So what's really happening is that we wanted to create a special key to get this basically system working. The special key was you had to embed a color such that that particular color can basically hide the policy in the ciphertext. Our intuition was that creating a single key is hard, but maybe we can create two independent keys. One of them has the color encoded in it. The other one is sort of just like opening the box structure to it. And we can use both the keys at the same time. You need both the keys to open the ciphertext. That's basically the analogy, a physical analogy that you can think of, trying to sort of basically merge two systems in a more holistic way.
Was there something special with the sampling such that the full version is still Lattice?
Yes. But
Okay.
yeah, absolutely. So seems like maybe we are done. We just need this interesting gadget and that's enough. But this is just one nugget of the piece and this is not enough. And let me just tell you quickly why we need some more ideas. And the point is that I cheated a little bit when describing the entire system. As Bo was sort of telling us that he said that, okay, hey, what about the system, the ciphertext and secret key sizes? They're very large in the system. I hate that from you. The reason is that look at A times X plus B. The number of rows of this matrix is the number of users. That means the number of columns is going to be, has to be much larger than the number of rows because I want to encode a lattice and that's the property that I need. Once you do that, then ciphertext size and the secret key size are going to grow polynomially with the number of users. And that's pretty bad. I wanted to avoid it. But not too bad. We still have basically the basic structure with us. And the idea is that for those who people are aware, say we use something called branching programs, which allows to sort of compress the communication or just the computation of this access policy into an interesting graph structure. This could be, I mean, for people who sort of know it in other senses, this is binary decision diagram. And we show how to sort of compress this computation. We can sort of just use this compressed computation and perform this graph structure evaluation. Now, clearly, when we have to perform this graph structure evaluation, we get this nice property that the width of this graph is small, so that the number of rows of this matrix A are going to be small. So we get around that problem. But how to actually perform this computation? For that, we have to really need to change the structure slightly. We have to make sure the secret key and ciphertext are a sequence of cascaded matrices instead of like single matrix multiplication. And we can sort of just extend these techniques, create some more lattice gadgets, extending the techniques that I've spoken about so far. And using all these things, we can also reduce the ciphertext size. But the basic crucial part is that these lattices provide us interesting guarantees trying to get information at the same time, hide information and get functionality. And that basically sort of just tells you about how to get data tracing from lattices. And in this long line of work, we were able to sort of get many other results by using the structure of lattices and using the structures that we developed in this work. And in the remaining few minutes I have, let me sort of just quickly tell you about some of the recent works that I've sort of been involved in. And I've sort of just done a lot of advanced cryptographic works, but maybe let's just, let me sort of tell you quickly about lockable obfuscation, and I'll leave aggregate signatures for later if we have time after the talk. But let me just tell you a little more about lockable obfuscation. So we already discussed about the scenario where obfuscation becomes interesting. One of the applications was trying to software patch code. And obfuscation, it basically says, it gives us a compiler such that the compiled code is going to hide all the implementation details and the secret about the program. For example, give me an algorithm that either sort of creates a quick sort algorithm or a merge sort algorithm. If I obfuscate it and give you an obfuscated code, you won't be able to tell which particular algorithm I used. That's basically the power of obfuscation. Taking it further, if I embed my secret key in code and give you compiled code, even then that compiled code will not tell you my secret, you can't read it. And in our work, we were able to build the first obfuscation scheme for complex programs. We can actually perform some interesting computation from standard assumptions. And since we again relied on these amazing lattice techniques, we were able to prove post-quantum security. And still to this day, lockable obfuscation is the most powerful obfuscation that we have available to us. proven from standard assumptions. And since our original sort of work, it has found tremendous amount of applications, even beyond what we imagined initially, to zero knowledge proofs, quantum extraction protocols, credential hiding login, and much more. And in addition to the amazing positive applications it has also led to many interesting negative results in this in the area. It has resolved some fascinating fundamental circuit security conjectures, which were open for a really long time. So it showed that advanced crypto not only sort of just can be sort of used to solve these interesting positive applications, can also be sort of used to resolve some fascinating conjectures in the area. And let me sort of just, in the interest of time, skip aggregate signatures, but just quickly tell you that in addition to building advanced crypto, I've done a lot of other work in cryptography, trying to build quantum cryptographic primitives, trying to work in security amplifications, and much more. And be happy to talk further about any of these particular problems if they're of interest to you, or anything beyond cryptography that you're interested in. I'm typically curious about everything that we can do using cryptography. In the remaining few minutes, let me just try to conclude and tell you what I want to do in the future. And then we can sort of open to a Q&A and discuss more things, maybe the other questions that were left in the talk. So in the future, as it's not hard to imagine, I definitely want to build more advanced crypto, really understand what lies on this particular island. What are our limitations? And I also want to focus on trying to get post-quantum security. And there's so many fascinating questions still open in the area, trying to build witness encryption or trying to get general purpose obfuscation for all possible programs that you can imagine. And it might happen some of these questions are more influential than other questions, just like trying to build obfuscator could have much more impact. But we have to try to solve all of these problems separately, because that's how we will have maximum practical impact. Because we know how to get signatures, digital signatures from public encryption, but that's not the route we go for. We build digital signatures directly because that's the more efficient route. Similarly, I also want to advance techniques in lattice-based cryptography. Today, we are in a very nascent stage in understanding the techniques of lattices and trying to understand the structure of what more advanced structures we can embed in them. And I think in the future, it's going to be very important to sort of study it more, because not only it gives us, it's the leading candidate for post-quantum standardization, it has very rich structure that I told you about that can sort of merge two things in a more synergistic way. And beyond that, not just lattices, but we also should also look at other sources of hardness, such as pairing-based cryptography, learning parity with noise, and other assumptions. Because relying on these other types of problems, it's going to be very interesting, because not only they're going to diversify the foundations of advanced crypto, but they're also going to sort of give us more structures. And these more structures are going to lead to more progress and letting us understand how cryptographic hardness can be used to sort of get these interesting applications. Just sort of as a quick remark, even as a project for DARPA, we were able to provide them a very efficient and practical data tracing system that they might have potentially deployed in practice, but that relied on pairing-friendly elliptic curves. Although it did not get all the best properties that the lattice-based solutions got, it got some interesting tracing properties, and they could be enough for some practical applications. So it basically shows that studying advanced crypto and cryptography basically across multiple sources of hardness is going to be very, very influential. And in addition to sort of just these specific areas, I also have some sort of long-term major agendas in my research. As I sort of just describing to you, trying to blend advanced cryptography with law and policy, that's going to open a great avenue, trying to close the gap between science and policy that is still sort of left out. Because public crypto is not sufficient to close this gap, as sort of we demonstrated using both obfuscation as well as using traceable encryption. So there's just much more progress to be had in trying to sort of just let people know, let legislators know that the things that seem magical are no longer impossible. They're actually feasible. You can get them in practice. And we can give it to you if you sort of ask us the right questions. Just tell us questions, we'll solve it for you. Even beyond that, I'm also very interested in pursuing decentralization as a general concept in cryptography. Because what blockchains over the last decade have shown us is that decentralization leads to easier adoption of concepts, cryptographic concepts. And we really need to even adopt advanced cryptography in practice. We really need to also look into decentralizing this cryptographic progress that we have had. And there's some specific questions that I can talk about more. But in addition to that, I'm also very interested in the conglomeration of sort of just, trying to use ideas from quantum information theory and cryptography. Because when I started the talk, I said, back in the day, in the ancient days, people relied on physical infeasibilities, our limitations of what was physically possible. That soon was sort of just forgotten about because, okay, hey, there's nothing that's physically impossible. But quantum information theory basically says there's something called the no cloning theory. It says that you cannot clone quantum data. And that's basically a type of physical infeasibility that we can use as a cryptographic hardness. And hardness is power, along with cryptography, to enable certain amazing concepts such as unforgeable, physically unforgeable money. That's basically undoable because you can always copy it. And lastly, but maybe not least, typically in cryptography, we have these two regimes. Either build cryptography starting from these amazing assumptions, or try to understand these assumptions. I think trying to understand these assumptions is going to be very, very impactful to sort of just really understand the limits of cryptography and how much progress we can have. Because without having this proper understanding, we won't be able to, we'll be simply developing different structures for different problems. And we might not be able to reuse those structures. And we have to cryptanalyze all these new assumptions that might come up. So having a more systematic study of cryptographic hardness, and maybe we can sort of just break down all the cryptographic hardness in basic complexity theoretic class separations. And that could be very, very fascinating. And with that, I would like to sort of just thank you for your time, and I'd be happy to take any further questions.
So any questions from the audience?
Yes.
I'm just wondering, in terms of the performance,
Mm-hmm.
how does this
Absolutely, absolutely. That's a fascinating question and a very important question, because we don't just want to say, okay, hey, this could have impact on society and not talk about efficiency. So for that, I would say it's like a two sort of bullet answers. The first thing is that some of these concepts, they were sort of just impossible or sort of unknown for so long that the first generation is going to be definitely infeasible or just inefficient, not infeasible, inefficient. Similar to what happened with homomorphic encryption about a decade ago. We had homomorphic encryption almost, I would say 12 years ago now, and now we are actually seeing how homomorphic encryption can be deployed in practice. IDASH competitions, Microsoft libraries, and so many places where progress is happening. That happened only because we had the initial feasibility that gave us a very impractical system, but yeah, asymptotically efficient. But yeah, we were able to sort of do more progress, have generation 2, generation 3 of those results, and that led to more progress. The same needs to happen with a lot of these advanced cryptographic systems. First, we need to actually show them that they're possible. Once they're possible, then we can ask the wonderful questions that how efficient can we make them? But the second answer to that question is that, are we basically lost until we basically get to those most efficient solutions? The point is that maybe we can revisit what it means things to be secure. For example, when I talked about traitor tracing, I said, you should be able to always catch someone if something is working. What if I told you, can you catch someone with say 5% probability? It's not good enough, but maybe it might be good enough for some applications. Maybe if it's like just military sort of database, then like 5% is just a lot. Nobody will sort of just play that particular chance, because if you do that, then the possible repercussions will be very, very large. And these types of weakenings of advanced cryptographic concepts, they are feasible. So the project that we have with DARPA that basically gave us a traitor tracing system with this weak guarantee, with this weak tracing guarantee, get all the efficient properties, you can actually deploy it. It's nearly the same size as other encryption systems. And we were able to say without any extra overhead, much overhead, we can deploy it. It won't give you the best thing, but until we get the best thing for you, you can still have something. So it depends upon which approach you want to pick. But I think just following along both these lines is important as a sort of a research agenda, trying to see how much we can optimize and what we can currently get with the current bandwidth constraints. If that may be, okay. Okay. So,
yeah.
Okay.
Hi, I had a question. Yeah.
Mhm.
It's regarding the blending the cryptography with policy and law. Who would be the team that would come together to blend this together to decide how the law would be enforced in terms of cryptography, and how much of this would be implemented using cryptography versus a pipeline of workflow which the users would be implementing?
So basically, if I understand your question correctly, we have to first take the first step, which is we have to notify and just at least let the legislators know, the people who are in charge of these policies and laws, and say, what you thought is impossible is actually possible. And tell it to them that this technology is feasible. You can use it. You have to be aware of it, because it's more about sort of teaching people what is possible or not. And then these things become basically usable. So rather than sort of just imagining how these things will basically come into practice, we have to first notify them and let them know, work with them, that these things maybe can be sort of refactored and we can sort of modify their potential properties. And that might make it more usable. But these things are actually possible. Once you sort of just let them know that they're possible, then they might get adopted. For example, it's the same thing is happening even in the space of blockchains. In blockchains, I think the Department of Commerce I would say about a couple of months ago, had like a sub-hearing committee in which they were trying to understand what are the energy impacts of blockchain. It's just the size of Argentina. I mean, I don't know how many countries, but it's like the impact, the energy inefficiency of blockchains is really large. So they were really interested in sort of just learning what other technological opportunities were available. And many cryptographers, they gave testimonies, congressional testimonies as part of those subcommittee hearings, letting them know that these other things are possible, which might not be known to the public or even the people who are sort of building these things. So there has to be some policy notifying people that you have to start using these technologies. You can't maybe put these things into law that you have to use traceable encryption. You can notify these things and sort of just let people know, and maybe let them pick. You have to make it available. Right now, it's not available because they're unaware. The first step is just to make them aware. And then we can sort of get to the pipeline of how we can deploy these things. If that answers your question, or maybe.
Yes, it does. Thanks. Thank you.
So there's another question in the chat, and the question is, why can't the attackers delete all ciphertext colors? It's a great question. And the reason is that the attacker doesn't even know what the colors are. That's basically the point. That's what I mean by secretly embed an access policy. If it knew the color, definitely, that was the problem. How can you hide the color itself in the ciphertext? And that's basically what we are able to obtain using this lattice geometry. Yes. Can you speak a little bit louder, please?
Yeah, the question that I have is for the cryptography testing.
Oh, encrypted testing. So the question was again, what are the possible applications of encrypted testing? Let me give you a very real world example. Suppose FBI has a list of suspects. It does not want to release the sort of the list of suspects because they're still suspects. You have not sort of just held them, anyone say, okay, hey, that person is actually a terrorist or a criminal. And it wants to sort of just deploy those particular list of subsets in sort of airports or other places where you can sort of inspect people. It would be wonderful if you can potentially sort of give it an encrypted way that lets you test whether that person was sort of encrypted in this list or not. So in a way, you can do partial information testing about encrypted content. Typically, we imagine encryption as like a black box operation. You feed everything in, can't do anything with it. Homomorphic encryption also says, okay, you can compute anything of it, but you can't recover anything of it. Encrypted testing says that you can recover something out of it, but I can define what you can recover. And that doesn't break security. That's basically one possible application of encrypted testing. But it has many other applications that sort of just related applications that you can think about. But even beyond, okay, maybe another simple example, encrypted mail. Suppose you get an email from Dean and you want to be notified, okay, hey, it's urgent. It's email from the Dean. Maybe you can sort of just do encrypted testing. Okay, if the email is from Dean, notify me, otherwise don't. So you can sort of just deploy that particular key on a server, and the server can have this particular partial key that just lets us recover this information, but nothing else about the encrypted email content.
Hey, Rishab, I have one question.
I had a question.
Maybe you guys can decide which one wants to go first.
Yep. So hey, Rishab. So I had a question regarding your traceable encryption. So you spoke about the lattice-based cryptography. So I was really curious about what are the elements in this lattice? Are they just randomly sampled real integers that are taken? And the second question to that will be, you also mentioned something about trapdoors, and how can we arrive at the optimal trapdoors? Because what can happen is you said that you need to have a condition that the best way in which the trapdoors can be defined for a private key are the short ones. How can we arrive at that? Because
absolutely, that's a great question, fascinating question, and that basically deals with the fundamentals of lattice-based cryptography. Mm-hmm. How can you sample, random looking bases along with a trapdoor? Because you don't just want to sort of sample the good bases and then generate a random matrix, because then it's not going to look random because you don't know how to randomize these things. This is basically where the beautiful work of ITI and soon after they had so many works, McCann Piker and Gentry, Piker, Nathan. They basically gave us a mechanism telling us that there is a way to sample matrices in a way such that you can sample along with some trapdoor information. And that basically at the same time, you can sample a random looking matrix that has no information about the lattice, just encodes a bad basis and these short vectors. Now, if the question is that how to sample this, then this basically is like another technical talk into it, because it's beautiful. It's a beautiful mathematical structures as these things hide and they actually employ. Yeah. But it's really fascinating, and it just has been, I would say, the founding principles of lattice-based cryptography and all the progress that we're having, that we have a mechanism to get these provably secure, these provably hard random lattices along with this chapter information. That is a beautiful concept that, yeah, I did not elaborate in the talk, but yeah, that's basically something that we crucially rely on for all this progress.
Awesome. So just to follow up on this, I think it was already asked in the room there. So yeah, tying to that, I also had a question about the latency of this entire thing, because if you imagine, right, the goal of this entire thing was to make it more commonplace. So I was thinking, like, now you're basically doing a lot of matrix multiplication, computing inverses, and so on and so forth. So how will this be feasible? I know you touched upon it on the previous question that was asked. So yeah, if you have any thoughts on that, that would be great as well.
I'll just maybe quickly add to that, the current solution that we have, it's the first solution that we had for this problem. So this one is definitely not practical. If you want to implement it, we tried to come up with some conservative estimates. The conservative estimates are going to blow up your mind. They still sort of work around, I would say, around hundreds of megabytes of information. That's basically the lowest thing that you can get for a ciphertext. That's not very good. Absolutely, I agree with you. But that basically tells you that at least this is possible. Maybe this 100 megabytes might make sense when the number of users is, say, 1 quintillion or something. We don't have those many users, but yeah. So, but still, for sort of reasonably sized users, 1 billion, 1 million, you still need to sort of optimize these tricks, these techniques even further, and trying to understand, okay, now this is feasible. Now maybe we can sort of just do more things. We can understand how to actually get this structured. By each passing day, we have a better understanding of what techniques we relied on for getting this particular system to work. And basically, with that refinement of techniques, we're going to get to these refined systems, which are going to be much more practically oriented.
Got it. Thanks a lot. Thanks a lot.
Sure.
I have a quick question, Rishab.
Yeah, so I think, you can ask question that, So
feel free to, if
you maintain another 30 minutes as a reception. But yeah, so thanks to the speaker again.
So Rishab, current blockchains have